Oh, I forgot my tea. All right, there we go. Much better. Let's get started. More weight loss. How exciting. So, we have to do a problem to start, I think. Let's go ahead and do that. So, let's say we have some generic reaction, and we're looking for figuring out what the rate law is going to be based on this. And so we mentioned yesterday that rate laws can only be determined experimentally. So you can't just look at this equation and say, yeah, it depends on A and B, and that's the answer. We're going to see that we have to look at data in order to figure that out. And very often we're looking at just rates of reaction over the same period of time, and we're going to vary the concentrations of our reactants. So let's say our little experiment comes up with the following data points. So and of course we'll have our units that are fairly standard. Let's not have that mess with our sig figs there. What is typically done is you'll vary the concentration of one of them at a time, and you'll see how that particular component affects the rate of the reaction. And so looking at these, we're going to try and somewhat reason with these numbers to figure out how the concentration is going to be changing, or rather how the rate changes based on the concentration changes that we're putting out. So by putting these together, we're going to be able to figure out the rate law of this particular chemical reaction. So what can we see here that's happening? So perhaps the easiest thing to do is to look at, here we'll have conditions 1, 2, and 3. If we look at conditions 1 and 3, we see that the rate does not change, right? We still have 4 times 10 to the 2 molar per second. I'm always going to say meters. Just forgive me if I do. And so we can conclude that, upping concentration of B did not change the rate. That means that B does not affect our rate, right? We've seen that experimentally. So it does not participate in the rate law. Let's just say that. So our rate does not depend on the concentration of B. All right. However, we can see that there is a difference between the first two reaction conditions, right? We see that when we have doubled the concentration of A, we've gone from 10 to 20, 0.10 to 0.20, we have quadrupled our rate, right? We can see that there as well. So when we double A is doubled, rate is quadrupled. Exactly. So Kevin has already done the answer here. And so as a result, we can say that in fact it's A squared that is going to be playing into our rate law. So you're absolutely right. So because a doubling has led to a quadrupling, that's squaring the concentration, right? And if we had, tripled the concentration, we would expect to see a non-upling of the rate, right? We should see, if we triple the concentration, that we should see a 9 times result with the rate, because this is being triple. What's it? Squared. There we go. As a result. So we're just looking at, 2x, or, if we're doubling x becomes 4x for the rate, that's 2 squared. If we had 3x leading to a 9 times for the rate, for concentration to the rate, we would also we would see that that's 3 squared, right? So it would be the same thing. So that would work as well. If we had a twice doubling of the concentration leading to 8 times the rate, that would be 2 cubed, right? So you're just kind of looking at these and analyzing what's the effect of doubling your concentration, of tripling your concentration, whatever you might be doing, to kind of figure out what the exponents are going to be for your rate law. And so Kevin is absolutely right. Remember that the rate is going to be equal to k times a to the m and b to the n, however many reactants you have. We've basically just deduced that m must be 2 and n must be 0 as a result of this. So our rate law, therefore, is just equal to Ka squared. So our reaction rate does not depend on the concentration of B at all, but it does heavily depend on the concentration of A. And so we can kind of figure out, what would the rate be when concentration of A equals, I don't know, how about 0.62? We can figure this out because now that we know our rate law, we have seen that we can we have rates that correspond with certain concentrations of A. Not necessarily spectator ion, it's just it's present enough that it just may not be what determines the rate. So it's possible that the rate is dependent on A doing something first, and then immediately B is going to be reacting with it as soon as A does its thing. For example, we're going to see that when we study reaction mechanisms. There may be multiple steps happening in a reaction that we just put as A plus B. But where A has to do something crazy, like maybe A has to break apart first. And that step is what's going to be kind of holding back the reaction from going forward. And so as soon as A breaks apart or whatever, B can react with it instantly. And so B really doesn't have an impact on the rate. We're just waiting for A to do its thing. So that could be an example. It could be a spectator as well. It could just be not really participating. That's another option for sure. But there are other options too. Cool. So since we do know the rate at several given concentrations of A, we could figure out what the rate constant is. Right, now that we have figured out our rate law. So if we go ahead and plug in some numbers from that table, we saw that we had a rate of 4 times 10 to the negative 2 when A was 1. 0.1, I'm sorry. 0.10 actually, if I want to keep my sig figs. Notice, let's actually keep our units in there too, because we might as well just address that while we're here. So doing so, we're going to solve for K. In doing that, I think we just get 4, right? Hopefully that's right, Kevin. Double check for me. The units, in this case, are going to be per molar per second, right? We're going to take molar per second divided by molar squared. So we end up with the units of per molar per second there. And since this is a constant, we can apply it now to a new scenario when we have A equals 0.62. And so if we know that the rate, here I'll switch colors for some reason. We have our rate constant times, I don't need to put brackets, 0.62 molar squared. Awesome. I like when I can do the math in my head. Of course, now I'm not going to be able to, but that's okay. Doing this, bust out our friend Google 4 times 0.62 times 0.62. And we end up getting a rate of 1.5. I guess this is going to be molar per second, as we should get. Hooray. And let's just, see if this answer kind of makes sense. So we've seen that this particular reaction, its rate depends on the concentration of A quite a bit. So if we increase the concentration of A, we're expecting a large increase in the rate of the reaction. And so our original rate at 0.1 molar was 4 times 10 to the negative 2. And now that we've jumped up our concentration, we ended up with a rate that also went up quite a bit. And so this is a reasonable answer, right? We're expecting this to be a nice reaction there. So this has worked out pretty nicely for us. Hooray. Hooray, makes sense. Right? We would definitely not expect it to go down or something. That's a hint that we've done something wrong. It's always a good idea to check the kind of reasonability of your answers. Cool. Any questions on that one? All right. Well, let's move on then. Let's do another one. And I actually want to, let me just take one from one of the books I have here. Because, why not? Yeah, let's do this one. Okay. I'm going to copy a bunch of data for us here. So, we have, here's our reaction. Basically just transferring an oxygen from nitrogen dioxide to carbon monoxide. Of course, the concentrations are going to be, or rather the units will be the same. And this time we're going to have 5 experiments for us. Okay. 5.1 times 10 to the negative 4. 1.02 times 10 to the negative 3. 1.53 times 10 to the negative 3. Great. And then now let's look at the concentrations of nitrogen dioxide. 0.350 times 10 to the negative 4. So these problems are always harder to come up with, off the top of my head because of all these crazy numbers. Of course, you may not actually need all of this data, but it's important that we make sure we have enough to figure out our answers here. (6.8 times 10 to the negative 8). 1.7 times 10 to the negative 8. 6.8 times 10 to the negative 8. All right. Tons of data. Let's work with it. It probably just took me 5 minutes to copy right there, right? So look at this craziness. So let's analyze groups of these. So let's look at 1 and 2, for example. We see that our rate or our concentration of carbon monoxide is not changing. We see we have a doubling of nitrogen dioxide. And in terms of rate, we have a doubling. So the first thing we know is that doubling doubles the rate. Doubling nitrogen dioxide doubles our rate. And so what does that tell us in terms of what we're expecting for the rate law? That tells us that our exponent should be just 1, right? If we were doubling NO2 and we quadrupled the rate, that would be an exponent of 2. Remember, we're squaring it. In this case, we're raising 2 to the first power. So it'll be the same thing. If we were to double it and we saw, a 8 times the rate, we would expect that to have an exponent of 3. Right? So because it's just doing the same thing, the exponent is going to be 1 there. All right. Let's go ahead now. Let's look at, how about 1 and 3? So in this case, we're halving the concentration of nitrogen dioxide. And indeed, we are going to halve the rate. So half the nitrogen dioxide halves the rate. That's the same thing as our doubling and doubling, right? So we already have that information there. So let's look now at 1 and 4, perhaps. If we double the concentration of carbon monoxide, that's double. Make sure you can identify that, right? We're moving up to a different exponent, so we really have 10.2 times 10 to the negative 4. So we are doubling that. We do end up with a doubled rate. So we also know that doubling carbon monoxide doubles the rate, which tells us that the exponent for carbon monoxide should also be 1. And we have this as well here. Let's go ahead and look at if we triple the concentration of carbon monoxide, we end up tripling our rate. Makes sense, right? Just like before, we have the concentration, we have the rate. This time we triple. So still have an exponent of 1 there. So really, we only needed kind of 3 pieces of data we would have enough to kind of figure this out. So we didn't really need numbers 3 and 5 necessarily, but it's always a good idea to just double check, make sure that things are working out. More data is not really ever a bad thing. So we have found out now our exponents are going to be 1 for each one. Therefore, our rate law is going to be K times the concentration of each one raised to the first power. So let's go ahead and solve for K. Let's do that. Why not? That's just going to be, of course, the rate over the concentrations. And we can choose any of our conditions. Remember, it's a constant, so as long as the temperature is not changing, we can use any of these. I'm just going to use number 5 because that one is the closest one for me to copy off of. So that's a rate of 10.2 times 10 to the negative 8 molar per second. We have 1.53 times 10 to the negative third molar. And then we had 0.350 times 10 to the negative 4 molar as well. Doing this, let's go ahead and figure this out. 10.2 times 10 to the negative 8th. Let's see if Kevin can beat me on this. Divided by 0.35 times 10 to the negative 4. Doing this, I get 1.90 times 10 to the negative 8th. If I've entered everything correctly. Looks like I did, so that should be good. Kevin, let me know if you get the same thing. Units again for this will be per molar per second. And now we can, if we wanted, 1.90, hopefully times 10 to the negative 8th. Wait, you're right. How did I... Oh, I didn't put a negative 4. That's why I put 0, 4. Yeah, you're right. Aha! I didn't make a mistake, though. That exponent was never there. So good. Awesome. So we have our rate constant now. So we can go ahead and apply this constant to some other conditions. Let's throw some out there. Let's say if we have concentration of carbon monoxide is 2.6 times 10 to the third molar, and nitrogen dioxide is 1.2 times 10 to the negative 4 molar. Let's see what we get. Just throwing out some random concentrations, we can see what we'll get here. How to apply this rate law. So, we know that rate is equal to K times CO times NO2, which will be 1.9 times 2.6 times 1.2. Doing this. Let's see if I can type this in correctly this time. No guarantees though. 2.6 times 10 to the negative 3 times 1.2 times 10 to the negative 4. Doing this, I get 5.9, I guess with all our sig figs, times 10 to the negative 7 molar per second. Let's see if Kevin gets that. Well, this one, I mean, hopefully I can see very clearly the exponent should be negative 7, but we'll see. Cool. There's another thing we can do this while Kevin is double checking. We can kind of figure out, if we wanted the rate to be a particular rate, we could figure out what concentrations we would need to get the rate to be that at our given time. We could use, so we're going to have two variables here. 5.9. Okay, great. I'm glad Kevin got the same thing. So we can apply this to another scenario. So let's say now we want to have a particular rate, and we want to figure out what the concentrations we would need of each one. Since this is multivariable, we're going to end up having a lot of freedom. We can just kind of arbitrarily choose one carbon monoxide or NO2 concentration, or we could just make them the same. Doesn't really matter. So, because we're kind of given that leeway here. So, or I could, tell you have to have this carbon monoxide concentration. But in any case, we would know that our desired rate would be our rate constant times our concentrations of CO and NO2. So we know the product of those two would have to be, hopefully I can do this part, 6 E negative 6 divided by 1.9. We just need to figure out some components that we can use to have our two of them equal to this number. So it's what? Times 10 to the negative 6, I think? Yeah. So we would want something here. Any of these numbers, we can choose any number we want for either of them and then just solve for the other one. Or we could just make them equal. Let's just make them equal. Why not? Who cares? Let's just say they're equal to x. So we can find any reaction conditions. So let's see, so 3.16 times 10 to the negative 6. We're going to raise this to the half power. Doing that, we get 1.8, we'll say, because we had 2 sig figs, times 10 to the negative 3 molar, so we could have both of them equal that. That would work. Or you can just choose some value for carbon monoxide, figure out what NO2 would be. That would work. So hooray! We have an answer. So we can do a lot of things with rate laws. We can find, concentrations to figure out a rate, or we can find if we want a rate, we could figure out what the concentrations would be. So these can be kind of useful tools depending on what you want to happen. So, let's say you're working in the industry or whatever, and, your boss says, I want, this many by whatever. You can use this idea of rates to kind of figure out what concentrations you would need to be able to produce whatever amount you want by that particular time. Hooray! Though these are more for instantaneous rates than average rates, there's some caveats there, but that's okay. We have better ways to figure out that particular problem. All right, any questions on that one? We've done a lot of stuff with that. Alrighty, well, in that case, let's perhaps move forward then. There's going to be something that's called reaction order, which is going to be an important way for us to actually work with these equations. And thankfully, this is an easy thing for us to figure out. That's just going to be the sum of all the exponents that you have in your rate law. Remember that, for example, we had, A to the M times B to the N. You could totally have more reactants. If we had another variable for our exponents, we could throw that in there too. These guys, the sum of the exponents will tell us the reaction order. So it turns out for both of the reactions we've looked at so far today, both of them have a reaction order of 2, meaning they are second order reactions overall. So we've seen that carbon monoxide plus NO2 turning into NO plus CO2. We saw that the rate was K times CO times NO2. And so we're going to see that M plus N will equal 2. So our reaction is second order. This is a second order reaction. You can have, whatever order you want. You can have 2.5 as your reaction order, or 0 as your reaction order, or -1 as your reaction order. You can have all sorts of various numbers. However, we're going to see that we're going to be able to work with 3 particular reaction orders much more easily than the others. So if we want to look at, for example, a first order reaction, we know that that would be the rate law for a generic first order reaction. Hopefully that's not too crazy. We remember that this was also the same thing as saying the change in concentration over the change in time, right? Nothing too crazy there. That's how this thing is going to work. It turns out that if you apply the magic of calculus to this group of equations, you end up getting that the natural log of your reactant at a given time will be equal to negative kT plus the natural log of your original amount. Your original concentration here and you will have your concentration at time t, natural log thereof. Here, let me actually, there we go. That's what I meant by that. So we're going to be able now to evaluate, at a particular time, what our concentration is going to be. And so we're going to have that component where we have the rate constant, and now we're throwing in the time variable as well. So with this equation called an integrated, I don't know how to spell, integrated rate law, we can use this to figure out concentrations at a given time. So let's go ahead. Actually, we don't have a first order reaction that we did yet, right? So let's just make one up. Why not? So let's say the reaction of H2O2 decomposition. Making it up. I don't know if it actually is or not, but who cares? All right, so here's our reaction. If I'm telling you it's first order, that means our rate law is this, right? First order, one component raised to the exponent of 1. Awesome. So let's go ahead and say that k equals 3.6 times 10 to the 4th power at this particular time. This is actually just going to have units of per second. Okay, I'm just making up these things, so don't actually quote me on this decomposition business. But for practice, let's go ahead and figure it out. So let's say we start with H2O2 equal to 0.246 whatever molar. And here, let me throw some other sig figs in there so we can deal with some actual numbers here. What is after 3 minutes? And let's throw some sig figs in that one as well. Exactly 3 minutes. Let's see how we can use this integrated rate law here. So, integrated rate law tells us that the natural log of, I guess, H2O2 at 3 minutes will be equal to negative kT plus natural log of, keep saying A, H2O2 to begin with. 0 again meaning time 0, so that's your initial one. So we can figure out all this stuff, right? Let's go ahead and plug in some numbers. So we know that the natural log of our hydrogen peroxide is equal to, K is going to be what, negative, or 3.61 times 10 to the fourth. Aha, we have a problem. We have 3 minutes, but our units of rate law or rate constant are in seconds, so we should have our unit of time also be in seconds. Hoo-hoo, done. There it is, 180 seconds. See how clever I was? Very smart. So it's going to be that. That's going to be our negative KT term plus the natural log of 0.2462. I should not be using brackets there. So we're going to now bust out our friendly calculator. Negative 3.61 times 10 to the fourth. Where was I? Times 180. Plus the natural log of 0.2462. See if this even makes sense as a problem. Did I get this? How did I get a negative number here? Oh, of course it's going to be negative, though. Okay, so this one I get... Natural logs can't be negative, though. Kevin, what do you get for this? Apparently I can't do math. So everything looks like it's input correctly. Negative 3.61 times 10 to the fourth times 180 plus natural log 0.2462. Kevin, tell me what you get. Oh, and actually, I think this is gonna work. I think we'll be okay, actually. No, this is gonna work. I'm mistaken. We're not actually taking the natural log of a negative number. Our natural log is a negative itself. We're okay. We're okay. So I get negative 6,498. 1, 2, 3. This is our crazy number. So we must therefore do e to that number, right, to get rid of our natural log term. The opposite function of natural log is e to the x, right? So this is going to tell us our natural log of H2O2 at time equals 3 minutes is that. So therefore our concentration of H2O2 is e to the negative 6,498,000, which will be, let's see if I can do this in Google. I get 0. Apparently it's a very small number. Yeah. It's a very small number. As you can see, we're putting this e to some really gigantic exponent. So it's approximately 0, I guess. Something really small. So again, this is just proof I should not be making up my own problems, because we're going to get 0 as our answer. So we're probably going to get up with some number with, some, 10 to the minus 9 or whatever exponent, where at some point it's just not going to even be detectable anymore. So pretending this worked, this is how we would use this rate law. So I guess I gave us too big of a rate constant. Times 10 to the 4 was probably too big to give you guys. So yeah, I apologize for that. Sometimes the problems don't work out, but that is how we would do it. Okay, so... don't worry, in your homework, the problems are written correctly, so we'll be okay there. And once we do stuff with the second order, we already have data to work with, so we already have reasonable rate constants there. So there we go. So basically, after 3 minutes, we have no hydrogen peroxide left. It is all completely decomposed, and we're done with our reaction. So that's awesome. All right, let's look at second order reactions, because we have more kind of data for those anyways. So a second order reaction can look like this, that we saw in that first example. Or another one could be K times A times B. These would be examples of second order reactions. Either one would work. When we end up doing the integration of these, we get 1 over the concentration of A is equal to positive kT plus 1 over our initial concentration. This is what happens when we integrate these. Notice that all these integrated rate laws are linear equations, meaning they kind of follow the form of mx plus b, right? We have f of x here equals mx plus b, right? These all kind of work that way, or y equals mx plus b, you can put it that way, where x is our time term. So these do follow linear things. So when you end up graphing these, you'll be able to identify a second order reaction by having a linear graph when you put it into this form. So that aside, let's not worry about that quite yet. Let's just see what we can do with this equation here. So here's the integrated rate law for second order reactions. Is that how you spell it? Yeah, law is good enough for second order. Let's go ahead and zoom up here to get some data. We calculated K for this to be 1.9. Well, we're going to use our same equation as before. We saw that K equals 1.9 per molar per second. And yeah, let's go ahead and do some math with this. So let's say, in this case, let's do time 60 seconds. Let's see what happens after 1 minute. If our initial concentration of carbon monoxide is how about 8.94 times 10 to the negative 4 molar. Let's hope this works. I don't think we'll encounter the same problem because we're dealing with a reasonable rate law with a reasonable concentration and a reasonable time too. So let's see what happens here. Actually we probably won't, because this is telling us here, let's do this. We'll have a really big concentration. And hopefully this will work out now. All right, so let's go ahead and plug this in and see what we get doing this sort of thing. So here we go. 1 over our concentration is equal to 60.0 times 1.9 per molar per second. This is, of course, seconds. Plus 1 over 8.94 times 10 to the second power. Doing this math, 60 times 1.9 plus 1 over 8.94 times 10 to the second power. Let's hope this works. I get 114.000 whatever. Probably, again, our concentration term is going to be really small, but who cares? Doing this, we're going to get CO is going to be 1 over 114. Whatever, how many zeros we had, we can do that. Just invert it. Apparently when I type this into Google, I get a whole bunch of law or US laws. Okay, this one kind of worked. Hooray. We do this, we get some small concentration of carbon monoxide left. And of course our units will be molar. Hooray, how many sig figs do we have? Looks like 3. So we're already okay. Awesome. We did it. Hooray. Awesome, awesome, awesome. So do we see how to use this one? It's just plug and chug. It's an equation. Hopefully nothing is too crazy there. Going with that. Shall we do another one? Perhaps? Why not? Let's go ahead and use our other one from before. We had where the rate was equal to Ka squared for that other one. That first one we did. I'm going to scroll all the way up here just to get the numbers again. To do our magical number, we had 4 was our K. So let's go ahead and... We have such big rate constants for all of these. Oh well. So K was 4 per meter per second. Let's say, let's see what the concentration of A will be at 14.8 seconds. Or let's just say, let's mix things up. Let's say that's going to be 0.894 molar. Let's find the initial concentration this time. Let's hope this works. I hope so. I'm giving you a really short time, so let's hope this all works out nicely. All right, so our equation, this is a second order reaction. Is this. So therefore, if we're going to solve for 1 over, or the initial concentration, oh my gosh, what have I done? That's going to be 1 over this guy minus KT, right? So doing so, we can plug in our values. Minus 4 times 14.8. We're going to, of course, need to invert this in a little bit, but let's go ahead and do it anyway. 1 divided by 0.894 minus 4 times 14.8. We get negative 58.08. That's already not a good sign. We shouldn't have a negative concentration. Wait, did I do that wrong? I don't think I did. Well, let's see what happens. How the heck? These problems are so hard to come up with. I don't understand how this could be a negative number. It shouldn't be. Oh, well. Suffice it to say, kinetics sucks. That's the answer here. So I guess I'll have to actually come up with like problems beforehand for us to do and make sure they actually work. That's not fair. I don't want to have to actually do work. All right. So with this, let's go ahead and solve for it anyway. So that's our 1 over our concentration somehow is going to be negative. Kevin, did you get a negative one as well? Just curious there. This shouldn't make sense. Oh well. Something's gone wrong. Well, whatever. If you do this, we're somehow getting a smaller number than we should. Something is weird here. Well, I don't know. So this is 2 failed problems now on me. You should get something bigger than what we started with, right? Somehow we ended up with getting less and a negative number. So I apologize. This has just completely gone to craziness. I got, when I calculated this, 0.017, which should not be the case. We should not ever get a negative concentration, and our concentration should be bigger than what we started with. So the answer here is never make up problems when it comes to kinetics. It's very unfortunate when that happens. So, where do we want to go from here? Let's disregard this for now. We'll come back on Monday and we'll do some real problems. I'll get some from the books, or I'll make up some that that will make sense. So this whole thing never happened. Okay, never happened. Cool. So that never happened. Let's just skip ahead. So, hooray. Let's look at a few other things. We're going to be looking at some graphs in this kind of chapter here, where we're going to be looking at how energy looks as a reaction progresses. So these will typically look something like this, where we have energy as our y-axis, and we're going to have reaction progress on the x-axis there. Often you could say this is time as well, because the reactions are happening over time, right? This actually has a fun letter. Forget it. I don't want to mess with that. It's xi is the Greek letter we use for reaction progress. I can do it though. It's squiggly like that. It's a cool letter. Yeah, there it is. How these look will be something like this. This is what a reaction coordinate diagram would look like. And let's say we have our, H hydrogen and chlorine combining to make hydrogen chloride or hydrochloric acid, depending what our environment is. And so we're going to see here that we have some important components of this diagram that we're going to be looking at. So let's say that this is our H2 plus Cl2 turns into a 2HCl reaction here. So we've learned previously that in order for these to react, they had to collide, they had to collide with the correct orientation, and they had to have enough energy when they collide for the reaction to happen. And we're going to see that in this graph, we're going to be able to find that component here. So it turns out that this energy here is called the activation energy. Here, let me not write that on top of the graph. This is the activation energy. That is the spark, as it were, that must be kind of thrown in there to make this reaction happen. And so what happens in this actual, reaction coordinate maybe, is we have our two molecules here. Normally in their happy states, they're just there as H bonded to H, Cl bonded to Cl. We saw that it's going to take some energy to break those bonds. So we're going to actually have to break our HH bond and our Cl-Cl bond in order to form the new HCl bond, right? And it takes energy to do that. That's our activation energy. So we're going to require energy put into this process to make it happen. And so we can actually kind of examine what things will look like at that activation energy. At this point, maybe, somewhere in this, we're starting to break our HH bond and our Cl-Cl bond. As we go up in energy, those bonds are stretching apart, they're getting ready to break. At this part here, we have what's called the transition state. Once we've reached that hump, at that kind of top of the mountain there, that's our transition state. And it's going to be kind of in between our reactants and products. So let me just let me erase time here. So a transition state is kind of in between reactants and products. So here the transition state might be where we have our individual bonds breaking and our new bonds forming. So somewhere in that process. So the bonds are partially formed between the new atoms, and the bonds are partially broken in between the old pairs. And so maybe this would be our transition state, for example. The transition state is often described, if we were to just write it out, would be something like this. We use this double dagger symbol to indicate the transition state. So whenever you see this thing, that equals the transition state. Transition states can't really be isolated, so we can't, just pick out this blob. We can't really isolate it and have this kind of weird 4-atom system. Once you reach the transition state, you're either going to go back to the products, or back to the reactants, or back to the products. So things can happen. Maybe they're going to decide the HCl bond does not actually have enough energy, and it's not going to form, and the things are going to go back to the HH bond and ClCl bond. Or things can go to the products, where we will now form our new bonds, and we're happy. Notice, by the way, also, this is an exothermic process. That's another component we can take away from our reaction coordinate diagrams. We see here that there's a difference between the energy of the reactants and the energy of the products, right? This would be our delta H term right here. That's what, here, let me put it here. So our products, as we can see here, are lower in energy than our reactants. That tells us we had an exothermic process. It gave off energy overall. So our delta H is also something we can get from a reaction coordinate diagram. So we have quite a bit of kind of information here, and sometimes we're going to see that we have all sorts of different ones. So we can have an endothermic process. We can have processes that have, I guess we can't ever start at 0 energy, huh? Let me try that again. We can have other reaction coordinate diagrams. So for example, this one is endothermic. This one is multi-step. So we're going to have 2 steps happening in this second reaction, where we have 2 different activation energies that need to happen. So we have activation energy 1, and then we have activation energy 2 here, for example. We would have 2 transition states. Happening there. And we're now throwing in another part. Let me use a different color, actually. Where you would be able to have something called an intermediate. And oftentimes you can actually isolate intermediates if you have a multi-step reaction. So if you give it enough energy to get through that first hump, but not enough energy to get over the second hump, then you can isolate an intermediate. So that's exciting. So you can figure out what's happening in between a reaction. Basically, you can see what's happening kind of going on step by step. So we're out of time here today. On Monday, we will come back and do a few more problems with the integrated rate laws. I'm going to have some that actually work out, because I think it's pretty crappy when things don't work out. So we'll get that to work. Don't worry. We do have one more reaction order that I haven't talked about yet that we'll put in as well. I just kind of got frustrated with the problems that didn't work. So we'll fix that. Tomorrow, if you're in the honors section, I'll be posting up your like kind of guidelines today probably for us to go over tomorrow. And then the week after that, we'll actually start doing our honors stuff. Otherwise, I'll see you on Monday. You do have solutions homework that's due on Sunday, as well as 2 of the lab simulations that are going to be due. Of course, if you have any questions, throw them out in Discord. I'll be happy to answer them, or you guys can help each other out. And yeah, with that, have a great weekend. Sorry about the little snafus today, but we'll fix them. So we'll go forward. All right, see you guys.